This is topic 9 of the Regents Physics syllabus, magnetism. And this section is the introduction to magnets and magnetic field lines. First, I'd like to talk a little bit about natural magnets that are found outside. Natural magnets, one type of natural magnet is called a lodestone. It's a type of rock, and you'll see that paper clips will stick to a lodestone because it's a natural magnet. Right? And they're found outdoors just like any other rocks. Now, there are elements such as iron, nickel, and cobalt, which can very easily be made into magnets because the properties of these elements, the way that their electrons are arranged, allows them to become magnetized very easily and to retain that magnetism and become permanent magnets. Now, what causes magnetism? Magnetism is caused when a charge moves. Let's take an electron, for example. When an electron travels at a constant velocity, it creates a magnetic field around it. Actually, let me back up just a second. The stationary electron, we know, has an electric field around it. The electric field is oriented toward negative, toward negative, toward negative, toward negative, toward negative. So the electron that is not moving has an electric field around it. When that electron starts traveling at a constant speed, all right, let's make it go in this direction, it not only has its electrical field around it, but it also creates a magnetic field that is oriented perpendicular and around the direction that it's traveling. So the magnetic field in this case would be looped around like this. The direction of the magnetic field would be perpendicular to the direction that the electron is traveling. Now, if that electron, while we're at it, if that electron, we'll call this constant velocity, if that electron is accelerating, it has its electrical field, all right, we'll call that E. It has its magnetic field, we'll call that B, and it also emits electromagnetic radiation, or light, some kind of light. So again, the stationary electron has its electrical field around it, E. When he's traveling at constant velocity, he also creates a magnetic field, B, that is perpendicular to the direction of motion. When the electron is accelerating, all right, A, he has his electrical field, he creates his magnetic field, and he also emits electromagnetic radiation or light. Now, we're not going to worry about this one. We've done that already. We're not going to worry about this one. It's advanced beyond our Regents Physics syllabus. We are going to worry about this just a little bit. How do we create a magnetic field? How do we make magnets? Okay, so magnets are created when electrons, when charged particles, we'll use electrons as our example, are moving. Now, we know that electrons are traveling around the nucleus of every atom, so they're creating a magnetic field because of that motion. And electrons are also spinning on their axes, like a little planet. And they also create a magnetic field because of that motion. Now, the problem with most pieces of metal, let's take a chunk of iron, for example, is that the electrons, all right, the atoms and their electrons are randomly oriented. They're all over the place. So whatever little magnetic fields are being created, they're all kind of canceling each other out. So you don't have a magnet. But if you put this piece of iron in a strong magnetic field, all right, now I'll draw the magnetic field here, right, north, south, all right? Magnetic field lines are drawn away from north towards south, away from north towards south, away from north towards south. So this is a magnetic field, a strong magnetic field, and I put my piece of iron into that strong magnetic field. What happens is it causes the little domains, the little atoms, and the electrons that they have to line up, and now you have a magnet. We have just created a permanent magnet from what was originally just a piece of iron. Right? The little domains are now all lined up. They're all working together. And you now have a magnet. Okay, now let's take a look at our magnet. Here's our magnet. Every magnet has a north pole and a south pole. If you cut the magnet in half, you don't get a magnetic monopole. You don't get a single north and a single south. What you get when you cut a magnet in half is you get two complete magnets. This becomes a south pole and this becomes a north pole. Right? When you cut a magnet in half, you get two complete magnets. You can't separate the north from the south. Right? That's important. Now, we said that magnetic field lines are drawn away from north and towards south. So, let's draw the magnetic field lines around a bar magnet. Right, this is called a bar magnet. Let's draw the magnetic field lines around a horseshoe magnet. This is called a horseshoe magnet. Horseshoe magnet. Okay, we'll put south here, we'll put north there, it doesn't matter. We'll put north there, we'll put south there. Okay? So, the magnetic field lines away from north towards south. Away from north towards south. Away from north towards south. We're drawing magnetic field lines away from north towards south. Away from north towards south. Away from north towards south. So there are your magnetic field lines for a bar magnet. Right now, how about the horseshoe magnet? Let's fix the horseshoe magnet. Okay. For a horseshoe magnet, all right, away from north toward south. Away from north toward south. That's on the little tip right between the two poles. Right? The north and the south are called poles, just like the earth, which we'll talk about in a few minutes. Away from north toward south. Here's where they start to bend. Away from north toward south. Away from north toward south. Away from north. Away from north. Away from north, towards south, towards south, towards south. There's your magnetic field lines for a horseshoe magnet. Okay, now, what about the Earth? Well, the Earth has a giant magnet inside of it. The Earth has a giant magnet inside of it. Now, I do want to draw something else first. Before we draw the Earth as a giant magnet, I'd like to draw the Earth's gravitational field to contrast it with the Earth's magnetic field. Okay? So we're going to draw G, the Earth's gravitational field, first. The Earth's gravitational field, you know, goes toward the center, toward the center, toward the center. This is the Earth's gravitational field. Everything goes down toward the center of the Earth. This is what causes masses to have weight. This is the Earth's gravitational field that we just drew. Now let's draw the Earth's magnetic field. The Earth has a giant upside down magnet inside. All right, so I'm going to draw the magnet. That's not real, that's just a little drawing. And since this is going to be the North Pole of the Earth, what we call the North Pole, the magnet inside the Earth is the South Pole. It's an upside down magnet inside the Earth. So this is where Santa Claus lives. Ho, ho, ho. He's got his beard. And the polar bears live up there. And this is where the penguins live. All right, so here's the penguins with their tuxedo. Okay? So here's the penguins. And here's Santa Claus. All right? So the South Pole of the Earth's actual magnet is up there at what we call the North Pole. So, let me just get rid of Santa Claus here now for a minute. All right, remember, Santa Claus lives up at the North Pole with the polar bears. The penguins live at the South Pole. So polar bears don't eat penguins. They don't ever see each other. All right. Away from north toward south. 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 So you see that the Earth's magnetic field is drawn very differently from the Earth's gravitational field. That's the Earth's gravitational field with gravitational field lines. This is the Earth's magnetic field with magnetic field lines. This concludes our section on an introduction to magnets and magnetic field lines. I'll see you in the next section.